Hello everyone. Welcome to yet another You Won't Believe talk. I tried to think up a better title, but apparently somebody else had already... Never mind. Can you hear me okay at the back? Great. You're about 30 meters away, so please add 90 milliseconds to any timestamps that you hear, or 90 nanoseconds to any that you see. I'm here with Jane Street, but this talk isn't work-related. Please come and visit our booth downstairs. The words are all mine, but the images are mostly from Midjourney, because AI is coming for your cushy SRE jobs. What's the king of the SI units? The second. So popular, it's even used in the US and Liberia. We'll look at the metrology of the second, from candles to atoms, and how your phone always seems to know the right time. Labels chosen years ago by nobody here today are essentially arbitrary. Tuesday, October, the year, my name, which work by consensus if we all agree. But how did we end up with these labels? Let's begin by discussing the calendar. The only natural divisions of time are based on the heavens. 1 day to spin the Earth, 1 year to orbit the Sun, and 1 month between each full moon. Computer science's 2 hard problems are naming things, cache invalidation, and off-by-1 errors, and we'll cover all 3. What year is it? It's 2024, but who decided? When? How did it catch on? Let's talk about years. When counting years, we have a choice of religious epochs, the start of the world, the birth of Jesus, the year of the Hijra, Muhammad's journey from Mecca to Medina. These can take a while to catch on. Dionysius only proposed the AD epoch in 525 AD. As such, I'm going to propose that it's now the 21st year of SRE. It will catch on. Local epochs count years from the reign of the king or the founding of the city. My favorite, though, are the apocalyptic epochs, counting down towards the end of the earth. This Roman altar to the god Silvanus dates from the year when Fundano and Severo were consuls. 2 problems with this naming scheme. We need a list of Roman consuls, and look how much space it takes up. That's just the year. Let's spin through 2,000 years of calendar reform through the eyes of some of the people involved. This is Meton of Athens, who gave us the Metonic cycle of 19 years, which accurately predicts the phases of the moon. This is Julius Caesar, who gave us the Julian calendar, with its regular cycle of leap years, shortly after which he was assassinated on the Ides of March. The Ides and other key dates of the Roman calendar are exceedingly complicated, so we'll just move swiftly on to meet Dionysius the Humble, born in Scythia, or modern-day Romania, who gave us Anno Domini year numbering and a way to predict the dates of Easter according to the 19-year Metonic cycle. The date of Easter was a really big deal, but being dependent on the spring equinox and the full moon is difficult to predict without a sound understanding of orbital mechanics. This is Bede, the 8th century Northumbrian cleric, astronomer, scientist, and historian. Bede was a strong advocate for Dionysius in his best-selling book, The Reckoning of Time, and I mean best-selling for the year 725, as over 200 copies still survive. I'm sure you all expected Pope Gregory XIII, whose reform to the is leap year function is still used today. The problem with the Julian calendar was that it misjudged the average length of the year by 11 minutes. That's an error budget of 0.002%. Pretty good, but not good enough for the Pope. The Gregorian calendar makes 2 simple changes. It drops 3 leap years, leaving 97 out of every 400, and it hot-patched the date, applying the rule change retroactively. This document, Inter Gravissimus, the RFC of its time, realigned the calendar. To correct over 1,000 years of accumulated error, October the 4th was followed by October the 15th. This important flag day didn't work. With only 7 months' notice, the Catholic Church spread throughout Europe, and an exclusive printing contract, not everyone made the October deadline or wanted to follow a Roman Catholic pronouncement. In a quote, probably from Kepler, Protestants would rather disagree with the sun than agree with the Pope. Everyone did eventually catch up, but some countries' adoptions are funnier than others. This is Francis Nicholson, who in 1710 led the conquest of Acadia against the occupying and Catholic French. You haven't heard of Acadia because it was renamed to Nova Scotia and the calendar rolled back to the Julian, causing a repeat of 11 days in 1710. This is King Charles XII of Sweden, where the rather unique plan was incremental rollout by skipping 11 leap days over 40 years. In 1700, splitting from the Julian calendar, there was no Swedish leap year. The next 2 leap years were accidentally not skipped, and the plan was scrapped, the Great Northern War or something. Sweden was still off by 1, so to roll back, a double leap year was declared in 1712, resulting in the only February the 30th in recorded history. And finally, here is Vladimir Lenin, who introduced the Gregorian calendar following the October Revolution of 1918. This would have been the November Revolution had Russia not been one of the last countries to reform. Over 336 years, Pope Gregory's changes finally made it to the civil calendars of the world. How's that for eventual consistency? Up next, what month is it? The usual definition of a lunar month is 29.5 days, but how do we construct a calendar out of and a half? Let's talk about months. The months of the Roman kingdom are the origin of the numerical names. Oct means 8, dec means 10, and so on. Later revisions filled in the unlabeled gap with January and February and redefined the start of the year. Next, Quintilis and Sextilis were renamed in honor of Julius Caesar and Emperor Augustus. Apparently other rulers tried the renaming trick, but it didn't last. Earlier we mentioned the Metonic cycle of 19 years. Why 19? It would be ideal if 12 months were equal to 1 solar year, but no, it's 12.4. Looking for an integer multiple, 8 or 11-year cycles come close, but it's 19 years or 235 moons that give the closest match. In the Islamic calendar, year numbering is simply 12 moons. Ramadan, for example, the month of daylight fasting, corresponds with December or June in different years. Lunisolar systems, such as the Hebrew calendar, inject 7 additional months throughout the cycle, keeping alignment with the seasons. The third and shortest natural division of time is the day. It's been Tuesday since midnight, but was that always the case? How long does it take the Earth to spin once? Wrong. It's 23 hours, 56 minutes, and 4 seconds, because as we orbit, it takes 4 minutes to spin a little bit further each day to keep the sun overhead. The Genesis narrative of creation is one explanation for a 7-day week. Another is the 7 classical planets, planet meaning wanderer, visible to the pre-telescope naked eye. So classical astronomy gives us Sunday, Moon Day, Mars Day, Mercury Day, Jupiter Day, Venus Day, and Saturn Day. Scientists are still debating whether Uranus is visible to the naked eye, but are too immature to decide. It's no surprise that Romance languages use Roman gods, but for Germanic languages, an example in the last column is Old Saxon. There's some correspondence between the gods, for example, Venus and Freya, or Mercury and Odin. Other language families are, of course, available. Many languages count up days from Sunday or Monday. There's no consensus. For example, in Portuguese, quarta-feira is literally day 4, or Wednesday. Weekdays in the various Gaelic languages have an interesting religious influence. Wednesday and Friday are the fasting days, therefore Thursday, Jerdine, literally translates as between 2 fasts. In English, the word day is ambiguous, so our word of the day is Nachtthemeron, meaning a period of 24 hours, and it's good for Scrabble. Icelandic is better, with dagur for day and solarringur, or sun circle, for 24 hours. When does Tuesday end? Choices include sunset, sunrise, midnight, and midday, and all of these have been used. The Battle of Trafalgar occurred on the 21st of October, but in the style of the time, the ship's logs record the 22nd of October because it was afternoon. So where are we? Or specifically, when are we? Our days are named after the planets, our months are mostly ordinal with an off by 2 correction, and our years are determined by Dionysius, advocated by Bede, and codified by Gregory XIII. A calendar works by common consent. If we all agree, then today is Tuesday. In the next section, we'll subdivide the day and abandon the heavens as the source of truth for time. clocks. Despite the popular misconception, clocks don't tell the time. They measure time, and as no two clocks agree, we're forever making adjustments to compensate for this inaccuracy. Is this a clock? Water flows into this shishiodoshi, or deer scarer, until it overbalances and noisily empties. It's a basic clock, even if nobody is around to count the ticks. Is this a clock? This clepsydra, or water thief, slowly allows liquid to flow into or out of a calibrated container. We can imagine the beginnings of an alarm clock, where a float is made to push or tip something over noisily. Is this a clock? A stick casting a shadow is the oldest and simplest way of measuring time. This sundial is more elaborate, where the small gap between the dolphin's tails indicates the position of the sun. My phone timestamped this photo at 1:15, so it's not bad. Are these clocks? The 1338 painting by Lorenzetti shows the first recorded evidence of a sand clock. A burning candle provides a very approximate indication of the passing hours. At this point, I invite you to think about some of the useful properties of the clocks we've just seen. Is it portable? What's the longest amount of time it can measure without intervention? Does it work at night? And if you had two clocks, how would we keep them in agreement? I'm so glad these are working. The first designs for a mechanical clock use gravity for the energy source and an escapement to regulate the speed. There's one design I want to make sure we understand, so let's look at the verge and foliot. A toothed wheel spins because it has a coiled weight wrapped around its axis. But it can't turn freely because two pallets block its path and have to be pushed away. The regulator is a long arm with movable masses. The poor accuracy mainly stems from the friction between the constantly moving parts. And this design also suits tall clock towers. Having a long drop available for the falling weight removes the need to wind up the clock so often. Replace the swinging arm with a wheel, and it can be made smaller. The addition of a spring makes the wheel into a simple harmonic oscillator, improving accuracy and allowing for miniaturization. This is more or less what we'd see inside a modern mechanical wristwatch. The next step in accuracy came with the pendulum clock, invented by Christian Huygens in 1657. So far, we've seen gravity and wound springs used as a power source, and we've seen foliot arms and balance wheels for regulators. A pendulum of constant length acts as a stable oscillator, but a disadvantage is the lack of mobility. It's too big to fit inside a watch and too fragile to take on board a ship. A pendulum's accuracy suffers from environmental factors. In this short pendulum clock, the primary pendulum is hidden away within the vacuum chamber on the left. The secondary pendulum is linked electronically to the first and contains all the timekeeping apparatus. This clock's design surpasses the Earth's rotation for accuracy. In other words, the Earth's spin varies by more than this vacuum pendulum. Precise clocks feature in several works of fiction. At the 57th second, the door of the saloon opened, and the pendulum had not beat the 60th second when Phileas Fogg appeared and in his calm voice said, "Here I am, gentlemen." Jules Verne is taking some artistic license by relying on the sub-second accuracy of a pendulum clock in 1872. Other fictional timekeeping tropes include Cinderella with its magical curfew, and of course the Gremlins, which must not be fed after midnight. Is this a clock? It certainly is. A precision tool for producing sound waves at 440 Hertz. The instrument can be calibrated, essentially by filing bits off until the desired frequency is obtained. There are some downsides. The clock doesn't run for very long and isn't convenient to wear on your wrist. I've got a demonstration of that here. A few seconds, so good short-term accuracy, but rubbish for measuring hours or days. Now let's make it smaller and out of quartz. Hello, tiny quartz tuning fork. This popular version is designed to vibrate at 32,768 Hertz, but we can choose the resonant frequency depending on its size and shape. This makes use of the piezoelectric effect, which works in two complementary ways. If we squeeze it, a voltage is produced. If we apply a voltage, the crystal deforms. Like pendulums before them, Quartz crystals are sensitive to temperature, but at this small size, we can put them inside a miniature oven. Holding steady at, say, 50 degrees C, it will always be hotter than the ambient temperature in the room. In what became known as the quartz crisis, the improved accuracy and lower cost of quartz led to a collapse in Swiss manufacturing of mechanical watches, which had previously held 95% of the global market. The classic Casio F91W is, to my mind, the perfect trade-off of cost and accuracy in a watch. Is this a clock? Yes, okay, it's a light bulb, but the specific property of this light bulb also makes it a very accurate clock, except we're missing the counter. This is the emission spectrum of sodium. You may recall from school science lessons that different elements have different spectral lines. Each photon from a sodium lamp at what's called line D has an energy of 2.1 electron volts, which is tiny. Photon energy is inversely proportional to wavelength, giving 590 nanometers, or what most people call yellow. We know the speed of light, so can express the cycle time as 1.968 femtoseconds, or its reciprocal unit, 508 terahertz. That's an accurate clock, based on the fundamental properties of the elements. Here's a diagram from the manual of a 1964 cesium clock. It looks complicated, but I believe in you. The trick for atomic clocks is that we're not measuring photons, rather using the absorption of the same spectral lines as photon emission. The cesium begins on the left, then the A magnet kicks out any atoms not in their ground state or lowest energy. The microwave in the center provides energy around 9.2 gigahertz, which excites the cesium. Magnet B kicks out any atoms which aren't excited, and the rest reach the detector on the right. There's a feedback loop between the detector and microwave, which allows us to find the exact frequency needed to excite cesium-133, which by definition is just over 9 billion hertz. This is the SI definition of the second. Modern improvements use strontium, aluminium, or ytterbium, and optical lattice clocks use frequencies in the visible spectrum, but it's the same basic idea of using physical properties to calibrate reference clocks. These clocks are now so sensitive that the current definition of the SI second takes into account local variations in gravity. You could build a lab at the top of Mount Everest, but please don't. Did nature place any clocks in space for us? Here are 3 examples. The sun reaching its zenith every day, the moons of Jupiter, which disappear and reappear around the planet at predictable intervals, pulsars are dense neutron stars which rotate rapidly. For example, the Crab pulsar, shown here, beats around 30 hertz. Clocks in space also include GPS satellites, which rely on precision timekeeping. In the final part of this section, let's talk about synchronization, or how to sell time. At 1 p.m. every day, the red ball is dropped, allowing ships within telescope range to synchronize their clocks. This working example is from the Royal Observatory in Greenwich. Another way to convey the time is a portable watch. Here's Ruth Belville, who continued the family business until 1940, visiting the Greenwich Observatory each morning, then traveling to her subscribers for a glimpse at this watch. The important idea here is that there's always a reference clock to synchronize to, unless you are the reference clock. We've got this far without mentioning time zones because you already know how annoying they are, and Tom Scott does a better video. Adoption of standard time can be seen as collapsing the sheer number of local references down to one large city. European countries are small enough to agree on a single reference, but the USA spans over 60 degrees of longitude, or 4 hours, and it was the demands of the railways which drove the adoption of standard time. It's worth pointing out that these are still whole hour offsets from the Greenwich reference, but that's just convenient, not required for standard time. For example, while it lasted, Dublin mean time was 25 minutes behind Greenwich. Paris mean time was 9 minutes ahead. There's no special reason that London time is better or worse, but for legacy reasons it was adopted by all the standards and is now pretty much impossible to change. How do we design clock synchronization at greater distances from the reference? This example from Paris is my absolute favorite. These Parisians in 1880 are admiring this fine clock provided by the Compagnie des Horloges Pneumatiques, which used a network of pneumatic tubes to pressurize a cylinder once per minute, pushing around a toothed wheel. Individual houses could subscribe to accurate time, delivered by their own personal pressurized air tube. Electronic schemes sprang up. For example, this map shows the distribution of time signals from London, using circuits already built out for telegraphy. Radio waves, predicted by Maxwell, but first observed in 1886 by Heinrich Hertz, inventor of the per second, are ideal for clock synchronization. It will work. This basic signal, just a preamble and start of our pulse, is more than accurate enough for human consumption. But for greater accuracy, the MSF radio signal, 260 kilometers away in Cumbria, uses an accurate 60 kilohertz carrier frequency and also carries a time code. This Smith sectric clock counts cycles of AC electricity directly from the wall socket. There's no time code, so it's manually set, but then it will run forever so long as the grid frequency is correct over the long term, averaging out fluctuations. The countries in green provide this time error correction in their power grids. In summary, we've seen that a clock is just a counter, measuring time inaccurately, running out of power, and needing frequent synchronization to an upstream reference. The invention of the pendulum clock surpassed the sun and earth for timekeeping purposes, and we now use fundamental and consistent properties of the energy levels of atoms to build clocks so sensitive they can measure the change in gravity on different floors of a building. Next, let's look at the ways to get time in and out of a computer. If you haven't been paying close attention, now is the time to concentrate. CPU contains a clock which can easily be read. This is the most code we're going to see today. And that's it. The RDTSC instruction reads the timestamp counter, which is the number of cycles since the CPU last reset. If we have a 3 gigahertz CPU, then TSC ticks are around 3 per nanosecond. But as these are cycles, neither seconds nor nanoseconds, do we need a lookup table for the cycle time? No, we can just ask. The CPU ID instruction is a library of detailed information about all kinds of interesting features supported by our CPU. Like a tree of knowledge, it's arranged into leaves. This leaf shows the frequency of the TSC, but wait a second, it has 2 values for base and maximum because modern CPUs have frequency scaling, turbo boost, and all kinds of tricks to jump the clock speed around. But not to worry, this CPU also has the TSC invariant feature bit, which guarantees that RDTSC presents a normalized clock tick at the quoted base frequency, ignoring turbo and sleep states. It's no good asking another computer for its TSC value. It reset at a different time and may tick at a different rate. We need to deal with UTC timestamps, and a naive approach, for example, the RFC 868 time protocol, is just to regularly ask the reference server, what time is it? There's some useful information here in the subsequent query, which may not be obvious. What size was the correction we needed to make? If we look carefully, whenever we set our watch, we might learn something about the underlying drift rate compared to the reference clock. What we're aiming for is not perfect alignment between clocks, but an understanding of drift rate. For example, when you tick 1 million times, I tick 1,000,005. In this way, we can infer the reference time without asking. Does this mean ask twice and we're done? Not quite, because there are other factors at play. Let's discuss a very analog example. Suppose my friend Claire owns an accurate clock and is happy to share timestamps with me for free. I write a letter each week asking for the date and time, and Claire writes back. Can you see the flaws in this approach? But can we infer things from the duration of the request? Perhaps Claire's reply was written halfway through the round-trip time. How consistent is the round-trip time? And is Teddy Bear Postman busy with other letters? We could improve matters by walking directly to Claire's house, writing down the timestamp, and walking straight back home to reduce jitter. Unfortunately, Claire is sometimes out, so I ask my other friends, Claude, Clark, and Clarissa, about their clocks. This way, I can tell more easily which have become unsynchronized to the others. In terms of reliability, clock selection is important to ensure that your references have not gone wonky. A single reference clock is like my watch. If it's the only available reference, it's the one you use. And yes, it's a Casio F91W. Two reference clocks might seem like an improvement, but when they disagree, how will you know which to trust? That's why I never leave the house without 3 watches, which allow us to filter out bad sources. 1010. This whole approach is analogous to the way computers handle timekeeping. The goal is to measure the drift rate between my own clock and an external reference. If we know the drift rate, we can correct for it. The most basic API our favorite operating system provides is time, which returns the number of seconds since 1970. It doesn't really matter whether the kernel learned this from a local RTC or from the internet or prompted us to type in the time on first boot, but the kernel is tracking the offset between the TSC and 1970, currently around 1.7 billion seconds. Counting into the billions since the year the Boeing 747 was launched is not so convenient, so we have other functions to convert epoch seconds to human-readable strings. But none of the functions discussed so far have a granularity smaller than 1 second. So if your computers can do more than one thing per second, we're going to need greater precision. This syscall is similar to the previous one, but with the addition of microseconds. Eagle-eyed audience members might spot that I had to jump through hoops and bypass libc to get this output. Back in kernel 2.something, Linux added support for virtual dynamic shared objects. Let me explain. You know what a dynamic shared object is, like libc, but a VDSO is a library provided by the kernel via a magic page mapping. Why go to all this hassle? Because using these syscalls is expensive, context switching into the kernel and back for something we may call many, many times. Have you ever noticed this strange corner of the process memory space? Where we'd normally have a file name, instead it says VDSO. What's inside this mysterious page? Well, it's readable memory, so we can dump it to a file and see. Aha, it's just an ordinary dynamic library, but mapped into the process in a weird way. Look at the function names: clock get time of day, time. These are the ways that we can query the clock without ever leaving user space. The other magic part of this is that the kernel exposes just enough internals to allow these functions to read the 1970 offset. Clock get time not only deals in nanoseconds, but pushes the boat out by exposing different clocks. The POSIX-defined ones are clock real time and clock monotonic. Real time is the normal clock, but monotonic is just a counter since boot, which never jumps backwards. Linux goes further, offering clock boot time, which advances during sleep, and clock TAI, which includes leap seconds. Leap seconds are a bit controversial. They're infrequent enough that developers have a few years to implement bugs in their software which only leap seconds can find. As such, they were voted out of existence in 2022, but the can kicked down the road to 2035. I worked on the team at Google, which smeared away the 2008 leap second by running the clock 0.01% slower. You can tick 86,400 times in 86,401 seconds. As this graph shows, the last leap was in 2016, and in 2020, the Earth started speeding up. So if we ever have one, the next leap second could be the first ever subtractive leap. Think of all the bugs. Now we know the various ways to read the clock, but how does synchronization work across the network? Lena's talk later today will cover this aspect in more detail, but I'd like to focus on a technology which might be new to you, named White Rabbit, or more boringly, Precision Time Protocol over Synchronous Ethernet. In this simple network on the left, each transmitter uses its own crystal oscillator. Gigabit networking doesn't have a separate clock pin, so each receiver uses clock recovery to read incoming data. But wait, these nodes are continuously connected and able to track each other's transmit frequency. What if we defined a hierarchy from reference clock down to ensure all the oscillators throughout the network were aligned? This is the idea behind synchronous Ethernet. The nodes are not free-running, but instead follow the upstream node's frequency. what is Precision Time Protocol. The big idea of PTP is to use hardware timestamping for improved accuracy. Why? Software can obtain a timestamp, then write a message, but can't know when it was sent. How long did it spend in socket buffers stuck behind other packets? The network card provides a timestamp, let's call it TS, which itself is transmitted in the follow-up message. The receiver calibrates the round-trip time using a delay request, which itself is hardware timestamped. PTP can work without synchronous Ethernet, but combine these two technologies and we have White Rabbit. So, how does your phone always know the time? Because it has so many options, directly from the cell provider, or via an atomic clock in orbit, or using tiny amounts of your data plan for NTP. The last bullet point is obsolete. Who sets their phone manually when it has all these other options available? There's so much more we could have included today, but we're now out of time. You depend on time. That's how it works. Did you believe it? Thank you.